Some of you had a question about LTL. How do you actually construct this automaton in general, or how these algorithms work? So this, how these algorithms work, complexity analysis, that's a whole separate field in itself. I just want to mention that if you really just want to use it as a tool, there is a standard, a reasonably standard library that's well maintained. We use in our group called Spot. It can generate these automatons, heuristic automatons for a variety of LTL fragments. I'll update this page over here later on with a link to this Spot webpage, so you don't have to copy the URL. Who is interested in this, in specifically the combination of LTL and low-level planning? One person too. So we have some code around that is not part of our software yet, I'm going to talk about in a moment, that will do this conversion and integrate it with the rest of our code. So I'll probe the student who has been using this to sort of make it part of our repository, so others can use it as well. Because it is kind of useful if you really just care about using it as a black box. It is a reasonably standard way of doing it. So there's lots of work in this area that we really don't want to replicate. Okay, so let's continue with the main event. I'll give you an overview of this software that we've developed in our group, called the Open Motion Planning Library. So what we aim to do with this is to provide a common core for all sampling-based motion planning algorithms. We noticed that people kept coming up with new variants and then comparing these new algorithms with the first algorithms like RT and PRM from the 90s and said, yes, we're doing better. Well, that's great, but of course you're doing better than something from 10, 15 years ago. But nobody was really doing a systematic comparison between this year's new flavor against last year's flavor, and it seemed like it wasn't really good for the field, but there were all these seemingly very similar ideas that wasn't clear what really were the winning ideas. And so we thought, well, we should really come up with a way to distill this into the essential building blocks and the essential heuristics that people use, and see what is really the novel thing for every algorithm. What does it really matter? Was it some low-level implementation detail? Was there really an overall idea that generalizes beyond some specific combination of things? And then there's lots of sort of secret sauce that over time people have developed that often gets missed when you enter this field for the first time. And I'll mention some of these things that can easily trip you up if you try to implement this from scratch yourself, but tend to affect performance quite a bit. So we really want to make sure that we reached sort of three very different audiences. And we want to use this in education, so we teach a robotics class advice. We want to make sure that undergraduates were able to use this. It has to be reasonably accessible. We also want to make sure that this is actually something that people within the motion planning research community were comfortable using. It was state-of-the-art enough, not sort of dumbed down in any way. And then at the same time, it would also be a useful building block for other robotics researchers who didn't particularly care about how every motion planning algorithm works, they just want to use it as a black box. In the same way that within our group, we tend to think of perception as a black box. Like we say, well, there's this Kinect sensor, we point at something, and somehow we get a 3D model of the world. How that translation happens, you kind of understand a little bit, but we also know that there's enough in there that we'd rather not know all the details. And that brings me to the final part, is that, well, we'd like to be able to say that this is also practically useful. And we really want to make sure that we not just have an intellectually interesting idea that really is basically not practical at all. So we have been working also on making this useful for real robots, that the industry would actually use. So we're not the only one who's tried to come up with this sort of standard motion planning package. Most of them, this is an earlier effort from our group that tried to do everything all at once, and it wasn't really successful. So basically, sort of adopted the Unix philosophy where we really do only one thing, it's only motion planning and nothing else. That has worked for us much better. So in a similar vein, there's this library called search-based planning library from Max Liegend at CMU, which may be closer to your comfort area when you're coming from AI. Max is also coming from an AI background. He uses A*-derived techniques to do search in continuous spaces. So it's rather than providing probabilistic completeness, he gives you some resolution completeness. So it's a different trade-off. Often he has very clever heuristics that makes it scale reasonably well to higher limits. Before I argued that, well, if you're doing any kind of grid decomposition, it's really hard to scale. But with the right kind of projections, you kind of make it work. But I won't say much about that. So that's still active, but the successful use of this library depends very much on having good heuristics. Whereas with sample-based planning, it will work, it might not work as well if you haven't added enough heuristics to it, but it will generally work out of the box without too much tuning. There's other libraries out there for sample-based planning. This is basically dead code that doesn't really work anymore. This is from the author of RRT, who has a library of RRT and some variants. There's a company in France that's doing work for Airbus and other French companies using motion planning for large assemblies. I'm not sure if it's still active or it's been, I think it may be bought by some other company. So these are specifically motion planning software packages. Then there's all these other packages that basically do robot software frameworks, more general purpose robot software. The most well-known one is ROS. Within ROS there's this MoveIt component that does motion planning. It tries to be a library-neutral interface between motion planning and the rest of ROS. It includes control and perception and everything else. But under the hood, really, right now, it's always calling OPL, our library, to do motion planning. But potentially, it's possible to add other planning libraries to it. So if you feel compelled to write your own planning library, then you could potentially just plug it into ROS and compare against what we have written. There's also OpenRave, which is a simulation/planning framework, also talks to ROS. There's various other libraries that have different capabilities. This is from a small company in Switzerland. This is for a project in France. I'm not sure how alive it is. It's another German group. These are both German groups. So all of them support OPL in one way or another. They all start off, at least the bottom 5 started off implementing their own planning, and over time they found out that, well, it's kind of a pain to have to re-implement everything. It actually was easier to just include a little wrapper for OPL rather than try to compete in terms of features with OPL. So we like to think that that's a good sign that basically we provide the right level of abstraction that people who have made wildly different choices in how everything should be structured in robot software and how the motion planning should be modeled, but they can still use our library one way or the other. So what this means is that initially it looks like the library doesn't do a whole lot because everything has been abstracted away to a high degree. A very abstract notion of state space/control space, a high-level representation of state validator, sampling, all these things are sort of defined in some way, except maybe the thing you care about most is the robot in the workspace. It seems a little bit counterintuitive, right? That something that does robot motion planning doesn't even have a robot class in it. Because that's really, there are so many ways to model robots. You really think of it as a bunch of sticks connected by joints, or you have detailed cat models, or, there's different choices you can make. There's different, people spend all their time writing kinematics libraries or inverse kinematics solvers. You didn't really want to sort of dictate that this is the correct way to model your robot. So we have an abstract representation that have all the right hooks, and we'll provide an example of how you can completely instantiate a real robot. in sort of application layer on top. The core library shouldn't tell you that this is how you should model your robot. Similarly, for workspace, well, let's just pick some label representation that should be good enough for everyone, right? But no, some people don't like that, and, especially if you're dealing with real sensor data, then oftentimes all you get is point cloud data. And it would be nice if, in some cases, you cannot simplify that to a mesh. You can actually do planning in just the point clouds. So, for that reason, you just don't want to say this is the correct way to model your robot or your workspace. But we realize that a library without robots or workspaces is not that useful. So we have built an application layer that I'll show a little bit. But that's really just for illustrative purposes, mostly. To really use this library, you should use it in combination with sort of a layer on top of it. Okay, so what are the essential things that a state space needs to do or have? Well, we like to say, well, from this space, I need to basically be able to allocate states. Right? I need to get new states. I also need to have a way to define distance. It can be different from specific spaces. Right? And you need a way to do interpolation, which is usually the most common way that people do local planning. Right? So people, instead of trying to find new fancy primitives, they pull back default option interpolation seems like a safe bet. Just do a straight line in your state space. And we have to have a way to test where the states are equal. So from this, we can then immediately derive some common subtypes. We'll just use Euclidean space, Rn. Everybody would like that probably. And rotation in 2D and 3D is also very common, so let's also model that correctly, especially in 2D and 3D, especially with lots of things you can get wrong. I'll come back to that later. Then finally, to create more complex spaces, we have this compound space type. Where really you can just take Cartesian products of other spaces. So we can basically say we reach a body motion. This is the product between R3 and rotation in 3D. Now we have motion in three-dimensional space. Or if we have a number of joints, we just take that as the cross product between rotation times rotation times rotation. So we can, for instance, read in a description of a robot. It says that it has these joints, and automatically construct the right compound space with just taking the cross product of each joint type. Similarly, we have something similar for control spaces. So remember that for cases where you model the dynamics, so for a car-like robot, we are not just planning in the state space, we're also sampling controls that we apply to our system. So once we have selected the state for expansion, we say, well, now we are applying control to our car to, let's say, turn a little bit or drive a little forward, and we need to be able to sample from that space as well. So here, there's not such a diverse array of options to model Euclidean space again as a reasonable choice for many controls. And we have a compound available, but so far we haven't found a need to really construct more complex control spaces than this Rn. It just doesn't seem to happen too much if you have controls that live in really weird topological spaces. Okay, then another primitive that we need to have is testing whether a state is valid or not. Usually that's defined by a layer on top of OPL. So this is the case where we don't say what this representation of the environment is. This is where it comes in. We really need to know how is a robot represented, how is a robot represented, and that's kind of hidden inside, behind this state validation class. As we have a way to say, well, given a state, here's a callback function that tells me whether a state is valid. So we have a layer on top in OPL that does this in a very for simple cases. For more complex cases, when you have robots with kinematics, then you need something like raw smoothing. So this function will check whether a state is completely free, but it will also check whether angles are within bounds, or whether velocities are within limits, and so on. additional information can also be returned. So some planners may be able to take advantage of this. If you use collision checking libraries, often you get more than a yes/no answer. You get the penetration distance or distance to the closest obstacle. Both bits of information can be useful. If you have penetration distance, then maybe you say, well, let's move along the direction to decrease that penetration distance and have a way to sort of perturb your bad sample enough to become a good sample. Or if you have a distance to the closest obstacle, you can say, well, let's maximize that distance so that I'm as far away from obstacles as possible. So there's some hooks in there that make it possible to basically build more clever samplers. So the most common stability checker is just a collision checker. That's all I talked about so far. We have a point cloud. Somehow we get a model from that, and just say, well, point clouds are noisy, so there's a difficult problem of even determining whether there is a collision or not. So that's sort of handled outside of OPL. There's a point cloud library, there's a collision checking library that takes these point clouds, and then we'll test with high probability whether something is complete or not. And then you have these triangle meshes, a little hard to see. The classical bunny shape, two rings that are intersecting. And there's standard libraries that will take care of that for you. So depending on the geometric representation, you may use certain libraries to help you with that. Again, because there are options, you don't want to build that into OPL. It's really sort of something else that an auto package does why would we reinvent it? So we have added wrappers for two different collision checking libraries in our package, but there are other options available. Okay. Now we come to sampling. We're looking at all the algorithms that have been proposed so far. We're trying to figure out how much do you need to know about the space and what kind of sampling do we need. The simplest is really uniform sampling. I think that's really all you need to do your basic sample-based planning. Uniform sampling is sufficient. But then there are all these other sort of fancier kinds of Gaussian sampling and other tricks that people have come up with. They're trying to figure out what's the common operator that we really need. One of them is just sampling nearby. So just sampling within some distance. So again, we need to use the property of distance associated with some space, and then be able to sample within that distance. Finally, Gaussian sampling is also useful to say, well, I want to stay within some Gaussian distribution around some node state. And in Rn, that's simple. Gaussian distributions over rotations become much more complicated. And it took me a couple of tries to get it right. It's not something that is sort of standard code that everybody uses. But it allows you to do now perform these heuristics that previously were sort of specific to just the Rn. Now they're done for some origin spaces. So we somehow abstracted away the tricks that were specific to one planning algorithm to say, no, it's just one little primitive that you can combine with other planners and other spaces. It really isn't something that is that specific as it was stated in that paper. We try to generalize all these things into the basic building blocks. Okay, so this is really not, I understand this may not be the most exciting thing, but I'm just trying to convince you that there's lots of generalization happening that makes it really easy to go from toy examples to real world examples, because we have provided this level of abstraction. But if you write your planner, your new planner, you say, well, I'm playing around with it in 2D, because that's easy to see what's going on, to then go and say, well, now let's run the ROS on my crazy PR2 robot or some other complex system, really should be no effort at all. Because if you basically use the abstractions the right way, then translating from toy example to real world example is no effort. That's the hope. So here's another example where people often get things wrong. So if you think of rotations in 3D, people like them. The easiest way to interpret rotations in 3D is, let's say, you rotate around X, and rotate around Y axis, and rotate around Z. You combine all three rotations, and you can cover all possible rotations, which is true. Except it doesn't cover it really uniformly. If you uniformly sample all rotations around X, minus pi to pi, and then Y, same thing with Z, you have a distribution that looks like this, where each rotation is now drawn as a little vector on a sphere. So you can think of the rotation around X and Y as latitude and longitude, and then the direction of this vector as the rotation around Z. And you get something that is very concentrated around the poles. And of course, if you have more rotations, things get even worse. So the correct way really well, the easy way to correct things is to represent things as quaternions, and there's easy ways to sample things just right. And getting this wrong matters because it basically, you need many more samples to get good coverage over here. If your solution requires you to use rotations in this part of the space, but you're heavily biased in the wrong part of the space, then you basically need more time. It really makes sense to do it right. And then we have similar issues for nearest neighbors. So notice a low primitive that is easy to do in toy cases, and the easiest cases are Rn. Much harder to do right when n is large, when you're in high-dimensional spaces, or when you're in non-Euclidean spaces. So we also provide some generic nearest neighbor data searching for metric spaces, or some fallback option for non-metric spaces. In non-metric spaces, there's really not much you can do other than an exhaustive search, or come up with an approximation that gives you still something reasonable. But yeah, this basically based on sort of the properties of the space that you can specify, for instance, it satisfies the child inequality or things like that. It will choose the appropriate nearest neighbor data structure. So it's just something less work to worry about. Now, before I talk about sampling, it's just something that we've done over the entire space. But in sampling these planners, typically we only focus on these valid samples. So in some way to create valid states. So for that, it's a valid state sampler, which in the simplest form is just rejection sampler. So we sample n times until we find a valid sample. That's in the simplest form. But you can also just say, well, I want to focus on samples with large clearance. So I sample n times, and I pick the sample that is furthest away from obstacles. So this, a reason that you can justify this is to say, well, these samples have better visibility. Samples that are further away from obstacles can see more of the surrounding space. But by the same token, you can also say, well, I should really sample samples that are close to obstacles, because those are most likely to be in narrow passages. And as we know, narrow passages determine the complexity of motion planning, so I shouldn't miss the opportunity to find something that's close to obstacles. So both arguments, there's validity to both arguments. But keep in mind that the boundary of the state space obstacles is of a dimension that is just one dimension less than the dimensionality of the state space. And so if you have an n-dimensional space, biasing towards the boundary is just saying, well, we're now biasing towards being close to this n minus one dimensional space. In 2D, it looks really good, but in ND, it doesn't buy you much. It's still a very high dimensional space. Okay. Then there's this generalization of goals. What should a goal be? It can be a simple state over here, which is how I presented the sample-based planning in the first half. But we can generalize this. Say, well, it can be some region we can sample from, or it can be some region that we just don't know how to sample from it, but we can measure how close we are. Or it can be just an abstract predicate. Another common scenario is where we have multiple states and you can sample it, but it may be expensive to sample from that. The classical example is where we have a manipulator, many degrees of freedom, and we only care about the end effector position. So I just want to hold the cup and hold it even. And there may be many ways I can do this, computing all the different positions for my whole body potentially, while I'm holding the cup straight. It's expensive to compute. So we have this little helper class that responds to thread and starts calling the inverse kinematic solver, which is the standard technique for finding a specific solution that satisfies a vector constraint. So since it's such a common thing to have, it seems there's a special class for that purpose. So we just generate a number of solutions. Maybe one solution might not work, but I say, I want to hold the cup even when this satisfies the goal specification, but at least for the even part, but also in the collision, then I want to be able to find other states. Or maybe this is collision free, but it's not reachable. Or maybe there's an obstacle between this configuration and my start configuration, and I cannot go from here to here. And so you need to be able to sample more than one solution sometimes. And as we saw before, we also want to be able to have these high-level goals that are now a little more abstract, where the goal is really just the property of the whole path. Right? It's basically, not just the end state, it's basically the end state of the path plus the corresponding trace in the automaton that matches the LTL specification such that the discrete part of the state that matches the automaton state is the acceptance state. So the problem definition of OPL is basically you start with one or more start states, so you can have more than one start state if you desire, and some goal object. It can be a goal state, it can be something more abstract. And then your planner needs to take some plan determination condition on the argument. It can be just a time value, right? Just terminate after at most 20 seconds. Determine whatever you have at that point. Or it can be some external event thing. Just, well, there's some other process that's guiding the high-level behavior. And then additionally, you need to have some clear method, figures of internal data structure so that the solve can be called in for a new problem. So notice what's not required is that you sample it somehow. Right? So we call this library open motion planning library. We didn't call it the sampling motion planning library. Because we always want to keep the door open to other types of planning. You don't have to use OPL, of course. It's kind of heavily biased towards sampling-based planning, but we always thought, well, we don't want to be exclusive. We don't really think that's a good idea for the community. It would be great if other people could show that their planner is just as good or better at solving some problems. But we don't really think there's the universal best planner for everything. So far, nobody has done this. Doesn't mean that you can't. We hope that at some point there will be other non-sampling-based planners in here. We're very much welcome that we're not hostile to that. Yeah, maybe that better. And we've implemented many planners. Other groups have started contributing their own planners. That's very nice development that takes some of the work away from us. People see the benefit that if you implement an algorithm in OPL, then for free you get that it works in Moll. For free you can now show that it works on many types of robots, and almost for free you see your citations go up because people have an easy way to compare it to your algorithm. Right? So it's there's sort of this network effect that once you start contributing to this thing that's already popular, then everything else that contributes to it will become more popular. But sometimes that's not how things start out. So other groups have developed their own algorithms first in their own software infrastructures. Often there's all kinds of legacy code. But we understand that, and we're happy to help in helping people transition their code from their own custom library to something that fits within OPL. RT star is a popular algorithm that provides optimality guarantees. So far, I haven't really talked about that much. I just said, well, we find a feasible path. There may be complex task specifications, but I didn't really address much the aspect of optimality with respect to some path cost metric. It can be path length, it can be path smoothness, path clearance, and all kinds of properties that you can associate with how much you like a certain path. So there's all kinds of optimizing planners, PR star, RD star were the first. Were originally implemented by the authors from MIT in their own code, but it really took off and became part of OGL, and suddenly people use it everywhere. So we have divided these planners into purely geometric planning, where we can use interpolation to go from one state to another, and planning with controls, where we have to have both a state space and a control space, where we don't have an easy way to connect pairs of states. We just have a way to go from a state, possibly towards another state, possibly just randomly nearby by applying some control. But even if you can't do exact steering from one state to another, you can still show that these planners are probabilistically complete. So this LTL planner seems like, well, maybe it doesn't really belong here, maybe it's its own category. Right? There's no reason that planning with LTL specifications should be restricted to systems that have differential constraints. I can imagine that LTL planning is still useful in purely geometric context, and that's 100% true. So this is really just a historical artifact that we're trying to correct right now. This is kind of where we started with our work in LTL, is to look at the combination of really hard motion planning, really hard chaos planning, look at the intersection. But there's plenty of hard motion planning left in just geometric planning, just increase the number of dimensions. So over here, we typically look at car-like dynamics, so relatively low number of dimensions. Whereas over here, we're looking at manipulation problems. So we have one of our students is now working on basically having a robot do manipulation tasks subject to LTL specifications. So one of the examples that he has used is that let's say you have a bartender robot. Eventually, everybody has to be served a drink. Eventually, everybody needs to pay. You need to collect the money. So those kind of things where you have to rearrange objects, but sometimes in a not exactly specified order. Or in a kitchen scenario, is another example. Eventually, you clear all the plates. So there's a room for LTL-based planning in the geometric side. It just hasn't made it as part of the library. Generally, it's just a long, painful process to really abstract away all the details and make sure that everything is clean enough form that it can be used by others. But these things just take time. Very easy. The paper from our group, don't expect that corresponding code is in the repository right the day after. Sometimes it just takes a little while. However, it does help if there's interest. So if you think that this is we have published or something that is useful to you, and you like to compare, it's always good to just send off an email saying, can I get access to this? Even if it's not quite ready for general consumption, sometimes we are willing to share, even if it's not quite ready for public use. Okay, so let me just give you an overview of how things all connect now. We have this notion of a state space, or state sampler. That's when you be able to sample the space. In systems with differential constraints, we also have this control sampler and control space, and a way to do this system integration or simulation, where we go from a given state, applies control for some duration, we get a new state, that's called the state propagator. All this information is combined with something called the space information. It also takes has a state validity checker as a member and a valid state sample. So all this combines all this information. And then, to further simplify things, we have this sort of very high-level container class that combines everything. It says, okay, here's a planner, here's a problem definition, here's a goal, it's also part of the problem definition. So if you don't choose these things, you don't have to choose a planner. It will be chosen for you if you don't specify it. Then eventually, once you solve the problem, the path will appear with the problem definition. Once the path is found, of course. And then there's some other things that the plan doesn't require. These coverage estimates and the projection of the space also need a way to sort of do projection. So you need to say, here's a new type of space, define your own space, here's how you do projection. In general, these things are automatically chosen if it's needed for all the predefined types. Same thing for motion validation. You can rely on the built-in one that basically does this discretization of a path. Say, this is how I validate a path. But in some cases, you may be able to do better. So let's show you just a minimal example. So this is for planning in 3D with rotations. It's typically known as SE3, Special Euclidean Group. So to say this is our space that we're planning in, or this code in Python. Yes, question?
The microphone is not working anymore.
Oh. The batteries may be dead. It was working initially, right?
There.
It's, the battery is definitely dead. Okay. Yes. How about let's just stand closer to this microphone? Maybe that helps. This one's not working.
Yeah, press the button.
What now? I'll just stand here for a moment until fresh batteries arrive. So this is Python code. We have the libraries written in C++. We have Python bindings. Just generally prefer to show these examples in Python just because it's less clutter in a way. No types and templates and all that stuff. It's, for demonstration purposes, it's easy to show these examples in Python. We have a space that we're planning. We left off some visualization stuff where maybe we'll specify some bounds when we plan an infinite R3 world. We have some bounds on R3. Then we declare some simple setup thing. Takes care of all kinds of auto select or tuning parameters. So we don't have to worry about that. Which is a whole other can of worms actually. There's all kinds of choices that you have to make sometimes that are, there is a reasonable choice if you know what you're doing. Most beginners do not know what they're doing. So if you make it simple, to say, well, you have the control to change everything you want, but if you don't specify certain things, then we'll choose a reasonable default for you. Of course, it's not necessarily optimal, but it will get you started. And this minimal example shows that there's very little parameter tuning that you need to do, not at all. Just say what space it is, just say that there's some high-level data classes. The function not shown here is state valid. Given a state to tell you yes or no whether the state is valid. Then we declare a start goal state. We set them in this simple setup object, and then we solve. If solved, print the path. That's it. In this case, simple case, the C++ code was very, very similar. Now we have the new in there. We have types. Otherwise, it's kind of the same. We have a new space, simple set thing. We have a set this callback function. Now we can do start goal states, set them, and solve again, and then print them and send it out. So the other part that I mentioned in the beginning, one reason that we wanted to do this, write this library is to make the comparison with other algorithms, or state-of-the-art algorithms, easier. Because in our opinion, a lot of work was published without really good validation that showed the novelty of the work. That's So we've developed quite a bit of infrastructure to make this comparison as easy as possible. And it really isn't a way to say, one metric to say, this is the best plan. Even if you limit it to a specific problem, There's usually many ways to look at it. With how, for instance, over here, I've shown a cumulative distribution function of how long it takes to solve the problem. So remember that just looking at averages can be very misleading. If you just look at how long it takes on average to solve a problem, it can mask this huge range of variability. And maybe you care more about the time it takes to get a solution with 90% certainty or 99% certainty. And then maybe some other plan that's on average slower, but is more predictable, can give you better performance. If basically time within a certain range is more important than average time. I mentioned before that there's all these optimizing planners. They tend to be asymptotically optimal, which means that they give you a solution at some point, and then keep refining that solution to a better and better one. In this case, we're trying to refine, minimize the cost, let's say path length, and we run different planners shown in different colors. What they are doesn't really matter, but you can see that all of them find better and better solutions. These curves go down, and you find confidence intervals for these curves. These curves are based on lots and lots of runs for each planner on the same problem many, many times. And we can give you some statistical analysis for free. You don't have to develop the infrastructure for that. You just set up your code. This is basically along the lines of the example that I just showed you. And you can get all this analysis for free. I'll show you a little bit more about that in the demo part. This is just another way to look at some other random property. In this case, the solution difference. This is a hard problem where none of the planners were able to find a solution, but want to maybe see how close to solving it did they get, how close to the goal did they get. This gives you a distribution of how close they got on average, or this is the box plots. So box plots show you the median, the 50% interquartile range, and 75% of the range, and sometimes outliers. I'm not showing here. So setting up this benchmarking stuff is really, really easy. So we have a command line tool for specific versions of motion planning. It's rigid body type motion planning, where you just edit the config file. But if you have anything that's slightly more complicated, you still easily do it in your own code. You just define this kind of setup object. You say, okay, I already plan our benchmark object, add a bunch of planners to it, and run it. Run with some runtime limit, some memory limit, run each planner a certain number of times, and then save the file. Then afterwards, this gets pre-processed into a database that you can then sort of view from different viewpoints. So you can automatically generate some plots, or look at the bounce time rate and upload your results and visualize the results that way. Then there's this little GUI that can be used with various types of motion planning. I'll demonstrate that in a little bit. So show you a path, sort of animate it, or here, sort of just show you all the intermediate states. Also show you, very hard to see here, but show you all the little red dots, all the states that's sampled. So sometimes that's useful to sort of figure out how your planner is behaving. It really is increasing density in the narrow passages, if that's what you want. Right? Or how the states are connected. I'll show you that kind of stuff. So here's some samples from GUI. Here's a car-like system. It shows you in green the interior part of the tree, and in blue the exterior parts of the tree. And it's sort of animating solution. This is the start, this is the goal. It's kind of a difficult case to planning. Very narrow passages, all kind of zigzagging kind of maneuvers. This is sort of a classic puzzle that you may have seen. These two nails that are sort of bent in some way, and only twisting in just the right way to untangle them. So it's a classic sort of hard problem. It turns out it's not actually all that representative of motion planning problems in general. So some planners that do really well here do really poorly on other problems. So just because you found a hard problem doesn't really mean that it's a good problem. So some benchmark problems, I think, should be predictive of broader kinds of problems. And if you really found an isolated worst-case problem, it's interesting, but it doesn't necessarily mean that performing well on that problem is going to help you solve other real problems much better. So it's always important to keep in mind that what you can really learn with particular development. I think this is a problem where we have second order dynamics. So this is first order, where we're basically controlling velocities. Here we're controlling acceleration, so it's much, much harder. This is a problem where you use physics simulator. It's basically, it doesn't know anything about where the obstacles are, really. It's a black box. It's just applying random torques to this black box and see what happens. And basically it's supposed to land on this red spot where there's a block in the way, and it's push the block out of the way. But it doesn't know anything about blocks. It doesn't know anything about gravity. It doesn't know anything about cars. And it's just probing this black box. And it's still able to find a solution where it has enough velocity to jump off the ramp, not fall off the cliff, and stop in time to land on the dock. And so that's an extreme case where, obviously, if you know more about the system, then you can develop some primitives and plan a little bit in a more clever way. It just shows that this abstraction mechanism is very powerful. Even if you don't tell a whole lot about your system, it's still able to find a solution. And this is just fun classical piano mover problem. This is originally how motion planning was defined. So we're actually moving the piano through the front door to the living room. But it turned out it's not actually all that hard. Alright, so there's a number of things to get started with piano. So first off is a website where you can find lots of information. OPL.org. There's lots of high-level documentation. It's not just the reference documentation. We have mailing lists. You can either reach us privately or just send it to the developer mailing list. There's user lists for public discussion, different repositories. Some people prefer Mercurial, some people prefer Git. Each set is your algorithm. I mentioned that we are using OPL in our class advice. We've also essentially, it's not just like here's a bunch of code, just do some programming. We actually did some educational assessments for specific teaching modules that assesses how well students are learning motion planning, internalizing motion planning concepts. And we've tested it out not just at Rice, but also at some other institutions. Shown that this really does help students understand the basic concept of motion planning. So if you're interested in this, if you're happy to teach or help in teach motion planning class, please contact us. We have a package, so ready with assignments and some set of solutions, all that stuff. It works for us, it works for some other people. I can't say it works for everybody, of course, but we found it useful. Okay, so now let's go to the last part where we'll show some examples of stuff that we worked on, and hopefully makes a lot more sense given what you know now about sending these others. Okay, so let's start with this GUI, pretty easy to get started. So we have this, in this example, we have a rigid body in a 3D scene. The start location is marked over here, the goal location is marked over there, and we're just asking for a collision-free path where this L-shaped block can translate and rotate. You can translate a little bit, or rotate a little bit if you want. It doesn't really matter. And then we click solve, and then we'll do this cursor. Yes, it works. Right. So now I'm showing states and edges. It's impossible to see. I should show a different example. Here's a classic narrow passage problem where it has to twist through a narrow passage. This is a little bit harder, even though it looks like there's barely anything there. I guess it's a good illustration of motion plan, and it looks like the other problem is much harder and much more obstacles. Really, here we have only one obstacle, one wall, and it cannot find a solution time given. So we'll just turn off state and edges to show states. In this case, it generated lots and lots of states, but wasn't able to get through. And as you can tell from the distribution of states, it was generating a tree in this case, where it didn't sample everywhere. It was expanding from a start state, and it didn't basically find a branch of the tree that went through this hole. So we can try a bidirectional version. It's a bidirectional tree line. Let's see what works in there. Great, it worked. So in this case, use color to distinguish the two trees. In this case, it's very clear that they're very well separated. In other cases, it might be interesting to see how far in your tree grew. So you can actually make a tree between the names of that column. So you see in the end, one of the green states got lucky, and it was a straight shot from somewhere on the left to all the way to the state on the right. So there's really not much to this. There's for each planner, you can configure certain parameters if there are parameters. So for PRM, for instance, you can control how many nearest neighbors you should try to connect to. What's a good done? Who knows, right? So from our experience, we figured out that 8 is a reasonable default. It's may depend on the dimensionality of your space, right? Maybe this is just the default that works reasonably well in 6D, looking at rotation and translation. But other cases may be a different number. A priori, it's hard to say. It's one of those cases where somebody has to make a choice. If you don't make a choice, we'll make one for you. There's another RRT star that has lots of bells and whistles. You should make some selection on how this should be configured, but you can change it however you like. But usually the defaults work reasonably well. You can also specify an optimization objective. So if you have a plan that optimizes something, we'll try to optimize that thing you specify. So by default, we can change the length, or optimizable length, or max minimum clearance. We try to create a path that as far as possible from the obstacles or mechanical work. Essentially, it's another way of more complicated objective. We can change the type of dynamics associated with our robot from none at all, which right now we're just doing rigid body planning. But we can also just change this to one of the built-in types. And not to say that these are the only things that OPL can do, but through a GUI, it's impossible. It's extremely difficult to allow arbitrarily complex dynamics. So we didn't really want to spend a lot of time in trying to make a parser that takes in a system of differential equations and turns that into code that now our planner can use. So as a trade-off, to still be able to do something interesting, we baked in some sort of standard dynamics that we might use as benchmarks, links, quad rotor, some interesting hard 3D cases, and first order and second order cars as sort of interesting 2D cases. Look at 2D case. Say we have a car in a 2D scenario. It starts over here, and as we plan around to get to that state. I'm not sure how well we'll do. Oh, did actually find that. So if I disable the animation, it will just show some intermediate states. I found a very non-obvious path, and it didn't really find the shortest path, but it did eventually get there. There's really no penalty for reversing direction. Sometimes using like cars, if it's facing a certain direction, it should go forward. But as far as planning is concerned, it's equal cost to go backwards or zigzag along. It doesn't matter in the plan. So sometimes you get very non-obvious paths. Okay, so that's one thing I wanted to show. So this. The same GUI is also available through the web. So you can, if you don't want to install any code at all, you can run on our server. All of you are doing this right now. It will probably be very, very slow. This is one of our machines in the lab that's running this. The OPL app code contains the code for the server as well, so you can essentially just host your own server. It has fewer dependencies, I think, than the GUI I just showed. So, depending on how comfortable you are with installing software, one might be easier than the other. It's more or less functionally equivalent. It's web version and the standalone version. Again, so select these built-in problems or upload your own meshes. So it's also possible with GUI. Again, select planners, hit solve, and find some solution. The one thing that this web version has that the GUI does not have is a link to the benchmarking stuff. So let's say you like this configuration, you can solve it. There you can see a solution. It's animated, same thing as before. Okay, this is an interesting problem formulation, interesting sort of combination of measures and star code configuration. Let's benchmark this. Whereas in the GUI version, you kind of have to save that configuration to a file and run a separate command line tool to do the benchmarking. The website allows you to just skip that step and just say, I'm going to run this planner, maybe add another planner to it. That's where I'm on the team. And then you add a list of planners, and then you say each of them can run for 10 seconds and run each planner 3 times. Not really a lot, but it's a benchmark. Now it's going to run in the bank on our server. When the results are ready, you can sort of look at them on this URL. So let's hope the server didn't break while it's gone. It looks like it did finish. That's cool that it didn't break. I'm always kind of worried about live demos, things are not working. Because the 3 is really not enough to make a statistical significance. We're just doing a very small number of runs so that we actually look at the results before it's lunchtime. Normally what we do is get some large number, run it 50, 100 times, come back the next day, look at the results, and compare against more than one time. Right, so this is the website, Planner Arena. Just go to more interesting example. If you just go to plannerarena.org, notice the URL specifically results that have a built-in database that has lots of runs for lots of different columns, so you can get a feel for what it can do. It's not to say that these are the benchmarks you should use. It's just some data to look at to get a sense of what the server can do. So here we're looking at a particular problem, abstract. Change it to a different problem. So cubicles is the one we were looking at before. I see that our outliers are marked. And by default, we're showing solution time. So what we care about, how fast is my planner. It shows you a little confidence intervals. You can change it to show it as, instead of a box plot, show it as a cumulative distribution function. Or another thing I didn't really talk about is this notion of simplification, post-processing of a pattern. So by default, one of the criticisms of sampling-based planners is that since they're using random sampling, they give you random crazy paths. It will never work. It turns out that finding a feasible solution is often enough to sort of fix it up afterwards in negligible time to get something that is high quality, it's locally optimal. So if you look at solution length, path length, you get some distribution. And some, if we include the results after simplification, now I say, just check this box on. It's basically shows you the difference between path length before and after simplification. It's huge. Right? Basically, the path after simplification is much, much shorter. And now, if you look at simplification time, it's 0.1 seconds, or compared to overall, the time was. The overall playing time, yes, a couple seconds up to more than 10 seconds. But in general, I mean, this is still a very simple problem. In general, the simplification is order of magnitude faster than the solving. So it really is sort of negligible overhead in terms of cleaning up the path, but it gives you a huge improvement in overall quality. And actually, so if you look at these optimizing plans, they do a lot of work to get you a high quality path from the beginning without all the post-processing. But what we have seen from our own experience is that if you just run some of these planners, these non-optimizing planners, just afterwards post-process it, that within the same time budget, you get a high quality solution if you don't optimize. You only do the post-processing. So, of course, your mileage may vary, but just keep that in mind that you get certain performance guarantees with optimizing planners, but in practice, you may not always get what you expect. And sometimes these heuristic approaches to afterwards fix up the path are so powerful that it's hard to compete with them. All right, so let's see, there's lots of other stuff that you can explore on your own in this website, but hopefully I give you an idea that this is relatively easy to use. You can define your own benchmark attributes. So all these widgets here, this whole website is populated based on what's contained in your database. We've documented the database schema, so you can add your own attributes, and it will basically add a new value in this benchmark attribute thing. You have defined a new thing that you care about. In the long format is also specified. So even if you don't use OpenPL, use your own library. If you produce log files or database in the same format as we have specified on one of the help pages, then you can compare your non-sample-based planner or whatever you use against whatever we have. So there is an easy way to go from really, the format is pretty basic. Okay, so finally, we should look at a few more code samples to give you a flavor of how you would set up and model problems. So this cubicles problem that you just looked at, if you were to write this in code, this is what it would look like. So this is again a Python example. So I have this. Hopefully this is legible. We started on, it's a little hard to see, but I have this Python module with OpenPL. Within that there's a submodule called CAP that basically takes care of this collision checking and all that stuff, about that kind of integration. We import that as our way. And say, okay, we're going to do rigid body planning in SE3. SE3 again is this space of translations and rotations in 3D. And then you're going to set the robot mesh to be this file, and the environment mesh to be that file. So we say it's the robot, that's the environment. Now we specify the start and goal state, which are exactly the same as we saw before in the GUI. Then we, in the end, we say set the start and goal state, and we specify some kind of collision checking resolution. Just for some extra information, we print this setup information. So after setup is called, it will initialize whatever you didn't specify. In this case, I didn't specify a planner. I didn't specify any parameters for whatever might take parameters, so it will choose some defaults. So I call setup, it will choose those things for you, and I can then print the setup object to give you a little bit more information to show you what it has chosen. Then I call solve at the end, simplify the solution. So that's all that you need to do to basically clean up that path. And then I extract the path, interpolate it finally. So this is useful for plotting afterwards. Right? Just interpolate it at some resolution. Then yeah, it's you get a nice smooth path. You plot it. And then finally, I print that as a matrix. Again, sort of facilitate plotting in some external software. Right? You can push this into MATLAB or Matplotlib, or create a tool for plotting data and print it as a matrix. And finally, I just do this check, path check, and basically just super samples your path and see if it's still valid, just to make sure. So the sanity check. Of course, not required. If you have chosen this cosine checking resolution correctly, then it shouldn't be necessary. In some cases, it's not a bad idea to just make sure. So if you run that program, when you run it, so no one was waiting on this, but it runs in a couple of seconds. It prints lots of stuff that's not legible in this color. In the end, it prints out lots of numbers. And this is the path. So each row is a state of the system. So can you guess what these numbers mean, each row? So the first three are position. The last four are the quaternion. So this, who has heard of quaternions? So what happened you are? So it's a four-dimensional representation of rotations. You can think of it as a point on a 4D sphere. Or you can think of it as an axis angle type representation. You have an axis rotation, another parameter that says how much you rotate about that axis. Yeah, generally you need four numbers, but these four numbers are unit length. So there's still only 3 degrees of freedom. Didn't gain any degree of freedom by switching to quaternions. So this is something that you can plot, that you can also save it to a text file and load it into the GUI. And the GUI can also plot. So you can, for instance, have your own code to produce a path and then save that this exact text to a file and then load it in a GUI for visualization. Okay. So this true that says the path is really valid. It's how you check text. So another similar example, again using the Romeo app layer. So you now plan for a first order car. And this space is called SE2. The state space, the state of the robot is described by X, Y, and theta. And we set some bounds in space so the robot is operating between -10 and 10, called X and Y. Rotation under constraint. We set some start and goal state. So basically the car has to move forward and upward by 2 units and rotate pi by pi. We set the start and goal states. Notice that in this case we didn't specify any meshes. So the problem is still not completely trivial. Right? Basically all the complexity of planning now is in the dynamics. You have no obstacles with an empty 10 by 10 square to go from 0, 0 in the middle to 2.2. All we have to do is find the right sequence of controls, which turns out is still not trivial. So this is just to show that you don't need necessarily obstacles to make the planning problem hard. Sometimes all you need is just complex dynamics. But it's still able to find a solution. Well, hopefully, it's randomized, right? So it's in this case, we have specified explicitly what the planner should be. I'm sorry about the colors, it's really not very visible. Do speak about that. Better? Maybe this is better.
Yeah.
Okay. So again, now we specify the flutter, solve, and get the path, print it out. So in this case, we may not exactly reach the goal. Again, because of this control problem, we cannot steer the system to the exact state. We specify some tolerance, in this case, for the goal. And we're going to be within 0.1 units of the goal. So if we exit solve, to get a path that maybe an approximate solution. In that case, we say that this is how close we got. Again, the output is again, so a bunch of numbers. The solution is approximate. But a number of numbers means something different. It's now our path is of a different type because we're planning with controls. So we are we have the x, y, data part of the state, the first three numbers, and then we have controls and duration. So we have two control inputs. How much we change velocity, the linear velocity, and how much we change the orientation of the car, and how long we should apply that different control. So we go at a certain velocity, in a certain turning rate, a certain duration of time, then we end up with a new state, then we apply a new control, and so on. So that's kind of how we parse these numbers. So you get complete information you need to reconstruct the path of a super-sample path. Okay. Now, let's say you are not interested in the OMPL app layer, you want to do just the core library, you want to do your own collision checking, your own integration. It doesn't make it that much worse. Suppose we are planning for a car-like system. This is really all that is specifying the dynamics of the car. So you take a particular start state. So this is not the start of the motion planning model, this is just the starting point of integration. So we at a given state in our tree, we then apply our control at a duration, and we obtain a new state. So in this state, we just say, with the new resulting state, we'll set the x value to be this formula, so the y value to be this formula, and this is just a solution of integration of basically car-like dynamics. It says control 0 is the velocity, and control 1 is the orientation, the change in orientation. So this is how much we are going forward. It depends on our current orientation and how long we're going forward and our velocity, and our current x coordinate, and the same for the orientation. In this case, collision checking is extremely minimal. We just say, is it the state within bounds? No collisions, no obstacles at all, just the boundaries of the environment. And the rest is sort of similar as before, except now we have to construct this extra space, the control space. We have a SE2 state space, and we have a two-dimensional control space, where basically we sample velocities and turning rate. And again, we want to restrict those to be within certain bounds, and get some magic to get the state in the right form, to get the function in the right form. This looks kind of intimidating the first time, because it's just a way to instantiate some arguments and bind the callback function to the right type. And then the rest is sort of the usual setups. Like a start state, a goal state, specify it. Okay, there's one little extra wiggle here. In this case, I use this high-level, low-level planner combination, a cyclone, where we have a high-level guidance. So in a high-level planning, we use abstraction to guide the exploration. So some of these other planners are just blindly sampling controls, constructing this tree that ultimately will eventually reach every point in the state space. That's but it may give you a really funny looking path. There's no guidance from a high level that says go roughly through these grid cells towards a particular state. But if we can define some decomposition, like define higher up in the file a decomposition of our space, it's really just a grid decomposition, we can help that, use Cyclone to help us guide the search. So this decomposition is only necessary to be defined if you use something like that. And the rest is sort of the same. We just call solve, get it solved, and print out the path. So this also finishes very, very quickly. And again, it's the same type of information you saw before. And finally, this is the most complex example I wanted to show is the LTL with triangulation. As scary as they are. We don't have a Python bindings for this part of the code just yet. So just to emphasize that this is a little bit more bleeding edge. As I mentioned, there is a tool that converts arbitrary LTL formulas to an automaton. Turns out in many cases we have already solved what the automaton would be. They were basically formulas of the type visit, P0, P1, P2, P3 in any order. That's a general kind of coverage pattern that we can generate the formula automatically for you. We know what the automaton, or generate the automaton for you. We know what it is. And other cases like that. So there's a number of factory functions that will generate the automaton for you for specific cases. Of course, not going to cover everything. So in C++, the code looks a lot uglier, because we have to do some typecasting. But again, we have some sort of, this code over here is implementing some car-like dynamics, except with a lot of immediate results. It's the same idea as before. You have a new x-coordinate, it's going to be the old x-coordinate plus control value times some duration and so on. It doesn't look as pretty here. This whole page here implemented before in Python, just a couple of lines. So our planning function is again very, very similar. So now we have the additional complication of an LTL specification rather than a goal state. Let's see. Since we have a more complex space now, we have a space that contains both the continuous part, is where we are in the physical space, but we also have a discrete part that tells us for how we got to a certain point in the continuous space, what the corresponding automaton state is. So we can keep track, as we are moving through the space, whether we have reached an accepting state in the automaton. So this works because we are basically building a tree, and we know exactly how we got to a certain state. If I randomly sample the state, there's many ways we can reach that point. But since we are constructing a tree, I know how I got to a certain state, so I can associate a unique automaton state with that state, with that low-level continuous state. Alright, so here we see the magic that we'll use to generate an automaton. We just say there's a number of states that I want to visit in specific order. So this is not the general coverage pattern. I visit these areas in any order. There's a specific order. Visit P2 first, then visit P0, and we allocate some automaton for that. It will do exactly that. So that's the co-safety formula. Then you can combine that with a safety formula. So at all costs, never go to P1. So we have another automaton for that. So now we have this three-way product between our abstraction of the continuous space. So this is you can think of this as the grid over the continuous space that will be used to generate sequences of grid cells that will serve as a lead towards the goal. So we try to find a continuous path contained within a sequence of contiguous grid cells that will satisfy the specification. And we take a product of that abstraction with the co-safety formula automaton and the safety automaton. And that will be the product graph. And we have a special type of space information. And again, a little setup to specify the start state. And we don't really need to specify the goal because that's implicit now. We basically just say, well, whenever we reach an accepting state, that's our goal. It's already contained in it. We don't have to specify it separately. Instead of saying add start state, we say add a lower start state. To further emphasize that we're only specifying the continuous part of the state, the high part of the state, the high level automaton state is inferred initially. So we don't need to specify that. This is just a little some further hint to sort of emphasize there's a lot more going on. It is a continuous search, a high-level search, and you're asking you to specify as little as possible. Then we allocate this special type planner, as I said, maybe doesn't quite fit the control type planner, but in this case it does. We solve this problem and eventually we find a solution. And again, when you print a solution, you could print also the trace to the automaton and reach order, things are done. In this case, there's a unique solution. You specified exactly visit P2 and then P0. It's not so interesting in what actually did happen. If you have a specification where things can happen in arbitrary order, you may want to print that out as well to see what it actually found. In this case, we only print out the continuous path, the lower part of the state. And that's again sort of similar as you've seen before. We'll print out some debug information, and then in this case, it didn't print it out as a matrix with more, so it's a pretty print format. Let's say, okay, found the control path, the first state here, it has these R2 components, this S2 component, and then I find these controls, so it's a little bit more verbose format. You can see that for readability, this might be great. For post-processing and knowledge, not so much. We have sort of matrix type format. This allows you to sort of see, okay, it's doing a lot of little moves, small durations to get eventually to the goal. But it's fun that even though it looks like a crazy long path, it actually the red almost instantly. Yeah, it's very quick. Okay. I think that's all the examples I had. So let's see. Just wanted to show you that there is a webpage, all the information here that I talked about. All the slides are there. Pointers to the software and other websites that we maintain. There's also the work funded by the National Science Foundation. If you have any questions at all, if you're interested in related work, please send me an email. I'll be happy to point you in the right direction. If you have any trouble with the software, please let me know as well. I made a virtual machine. If you really don't want to bother with installing packages, if you're willing to download that, it's also linked on this webpage. So you can, it is possible to install on Windows, it's more of a pain. I think in newer versions of Ubuntu, Linux, Debian, and Fedora, you can just get it through your package manager. Again, it'll always be the latest. You can get some version of it, but if you really just want to play around in the sandbox, this virtual machine is not a bad way to start. Okay, I think that's, I'll stop here. Take any questions.
Thank you.
Question?
Can you raise your voice?
Okay, so in most of the examples you have taken the state space as usually the task, because the usually space where the task is taken executed. Just want to ask you that in some literature I've seen that usually they take the state space as the joint space, for instance, right? Especially when you are working with industrial robots or serial manipulators. But I mean, this usually gives an overhead of you have to translate obstacles and everything to the joints, which is quite tedious to check the relation.
Yes.
Whenever I ask them about why do you do this, they say, okay, this is more, you can avoid similarities and all these things. But according to you, which one would be better? Is it better to plan to the motion in the task space, or is it better to the joint space?
I would say joint space, or depending on what you care. So if you typically, with many industrial manipulators, there's some redundancy. There's 6 degrees of freedom in an arm, and the end effective pose is also 6 degrees of freedom, about position and orientation. So you say, I want my manipulator to move through space. So when you say planning for pathways, I assume that you mean planning for the end effect. That's what you're really saying. And then one way to do this is to say, I'm only going to plan for the position I use an inverse kinematic solver to solve what the degrees of freedom should be to find a particular end effect force. And you can do that. However, most inverse kinematic solvers that I know of will give you just one solution, or maybe a couple that are maybe not uniformly distributed over the solution space. So for instance, if I say I really want to have the end effect position here, but I still have infinitely many inverse kinetic solutions that I might not sample if I call my case solver. Whereas if it's sampled in joint space, I'm guaranteed that I will have good coverage over all the solutions, and sometimes, depending on what the arrangement of obstacles is, I may really require only one of them. So for completeness purposes, it may be necessary to sample the joint space. In many cases, though, it's not so cluttered. Sampling in an end effect space, in the path space, might be just fine. Yeah.
I think this is usually just, I know some inverse kinematic solvers typically based on Jacobians or everything,
right.
where this is actually handled, where you can actually deal with the dependencies and everything, like at a local level, obviously, like if there's an approaching obstacle or you want to put some other cost functions or something, you can actually add up the null space velocity and easily handle it. So you don't have to really, search in the whole space.
Well, locally yes, but not if you are in a different topological class. So basically, if I have a choice between what's classically called elbow up or elbow down, but really I cannot continuously vary my arm position from up to down. Well, in this case, I can because I have 2 degrees of freedom in my shoulder. But if I go from a position where this, right here, or to this, and there is a wall over there, I cannot continuously vary the joints from here to there without colliding with the wall. So I cannot locally fix things up. If I happen to have to go from, let's say, this state to some other state over there, my case solver returns me this solution, whereas I really should have found that solution because afterwards I need to go here. So it's, IK will get you some of the way, but to the best of my knowledge, it's not a complete solution for everything. In certain cases, it's possible to find analytic solutions and really enumerate all the different solution classes. Sometimes that's how robots are designed. They're designed in such a way that you can find an analytical solution and you can enumerate all the different classes. However, if you look at the more complex, the humanoid robots, there's very many degrees of freedom, lots of redundancies. It becomes more and more difficult to rely on IK alone.
So in this case, what is the kind of overhead that we are looking in terms of translating obstacles from the task space to the joint space?
Well, typically, doing inverse kinematics, the call to the inverse kinematics solver is much, much more expensive than a call to a collision checker. And collision-aware inverse kinematics is even more expensive. Right? If you want an inverse kinematic solver to give you solutions that are also collision-free, it becomes tricky. Generally, just think of IK as a lot more expensive than just randomly sampling.
Anyone else have?
Is there a question?
Okay, so you talked mostly about motion planning. So two questions pertaining to the interface to the symbolic part about motion and task planning, and actually something is about geometrical planning. So one question is, so what is the state of the art of putting these two things together, let's say the symbolic and the geometrical part? In part you talk about that LTL is symbolic, but probably the sort of things that you can do in this way are dealing with relatively small automata, not with the sort of spaces that normally people in AI planners handle, okay, that's huge combinatorial spaces. So one question is about sort of the state of the art and the challenges there. The second is about the pure geometrical part. that is not static. Let's say that in order to go from one place to the other, so you need to push objects out of the way. So in some sense, the geometrical world is not static except for, and not, but there are other things that change as well. So apparently motion planners cannot do that, right?
They can. You have to have a richer notion of the state of the world. You're still, okay, so let's start with the symbolic plan, the state of the art. There are different views of where you want to push the complexity of planning generally broadly. So one part is in the task specifications of what kind of tasks you can handle. So there has been some renewed interest in set solvers, and using set solvers and S&T solvers for high-level planning. So we've been working on that as well. There's all kinds of other heuristic search techniques. It's pretty broad, depending on what community you're coming from, or how you see this problem.
But the key issue is the interface, right? So,
yeah.
So because in principle, none of the solvers is doing the two things together. Okay, both the geometrical and the symbolic one.
Yeah. So in the S&T solver case, what we've been doing is basically finding a candidate path to policy, and then using the low-level planner to find counterexamples to refine our model, and in that way we iterate back and forth. But this interaction is still very recent. I don't think that we have to finalize it. The overall architecture that we have happens to work well for us. I think there's a lot of value to that, so that there's a two-way street between the high-level and low-level planning. But there are other groups very well known and well regarded, Leslie Company and Johannes Levers, who have pushed this very AI-centric approach to basically using all the heuristics from the high-level plan to vector search, and are relying on low-level primitives that can then suggest how to do low-level planning. They've been very successful at that too. So it's, what I've presented really is a particular view of how task and motion planning can be combined. I should say that this is not the only way to do things. I mentioned some references at some point in the slides. I really encourage you to sort of do your own exploration. This is really not supposed to be an all-encompassing world view. I do believe in our view that it's useful. It's there. But there are other ways to do things. And you make different sacrifices, depending on where you think the interesting complexity of the problem lies. The second question was
about, for instance, when you have to do motion planning, but the world is not static, okay? You are supposed to push things or to, let's say, even do geometrical operations. Let's forget about symbols, okay? Just pushing things out of the way, for instance.
Right. Yeah, so it's still, you can still think of it as kind of AI block world, right? But now you have blocks in a continuous world, and you still need to satisfy some specification that you need to get the role need to be, but some blocks need to be moved around. So it is possible to still use low-level planning, and you definitely need a high-level guide. You can't just randomly bump around things or manipulate things and hope for the best. You need to have an overall guide, and this is something where we have made progress with the combination of our task planning and low-level motion planning. There's also a lot of interest in using learning techniques to figure out what makes sense to rearrange in this way. And the trouble always with reinforcement learning type approaches to the generalization is that if you learn to rearrange objects for this particular task, you really not work
yeah, but I mentioned this specific problem because it doesn't involve any symbolic part. It's all geometry. Okay, so pushing things out of the way, you're just the configuration of some objects. There is no, it's not a combinatorial symbolic space.
It is in a way if you, well, yes, you can think of it as, okay, you just want to get obstacles out of the way to...
This is just needed in order to get, it's not part of the description of the goal. The goal is to get to the other side. So just find that there are things that you can push.
Yeah. So there's different ways to go about it. If you, let's forget the box wall, if you really think about just trying to only focus on the geometric part. One way to formulate this is a constraint removal problem. If you think of, let's divide the world into static obstacles, the walls, and movable obstacles, tables and chairs. And we are saying we want to find a path for this robot that involves moving as few tables and chairs as possible. And so we first try to find a collision-free path that doesn't work. Find a path that goes through one table, so okay, now we have to move the table and we have to find a place for the table. There's work along these lines that we solve that problem. Just try to figure out a way to find a path that involves solving fewer sub-problems. So it's still a hard problem. Just finding the minimum set of pieces of furniture to move around is going to be hard. So, and then on top of that, we still have to solve the motion plan problems associated with that.
Any other questions?
So we have been working with open-wave environment in our lab, and recently we switched to OMPL and moving environment. So one good thing about OpenWave was that it has a lot of feasibility checks. So it can do the collision check as well as gas stability check, and then there is an inverse switchability check as well. So does MoveIt have this gas stability check or reverse check? The gas stability check, so you can check whether you can do the manipulation in the right way. I mean, you can check for proper gas, and then you can check whether you can get a pause before even picking up something, that whether the robot will be able to pick up something.
I'd be surprised if there wasn't something. It's not part of OMPL, but there's a component to move it called grass bit, right? It's I would be surprised if there don't have any grass metrics built into that.
Okay.
Another answer to your question is, well, you could use OMPL with open rate if you use it prefer. Not either or. I'm not an expert in grass bit, but I would be surprised if there wasn't something.
I think we should close it here, but Mark will be around today, right?
That's it.
So
tomorrow morning.
yeah, so we can continue to chat. Well, thank you again very much.